is an associate professor in the Department of Physics at the University Autònoma de Barcelona and a senior researcher at Catalan Institute of Nanoscience and Nanotechnology. His research focuses on the formation of unique amorphous structures and the study of the thermal structure and electrical properties using advances technique, including fast scanning nanocalorimetry. Today, Dr. Cristian Rodriguez-Tinoco will present experimental results of thermodynamic properties of vapor-deposited ultrastable glasses. Such studies are essential for understanding thermal transport in glasses, as well as other fundamental properties of vapor-deposited materials, including the role of strong anisotropy. Dr. Rodriguez-Tinoco, many thanks for accepting our invitations for today. We are very glad to have you with us, and the floor is yours.
Thank you very much, Maxim, for the introduction and for inviting me to these seminars, which I think they are very, very interesting. I don't know if you are, I think you are seeing my screen. I have some problems while sharing it in presentation mode, but I guess you can see it all right, no? Let me know if not.
Yes, we see. So you can switch the slides.
Okay.
All is okay.
So yes, as Maxim already said, I'm going to talk basically about ultrastable glasses, no, which I consider as a route to answer some questions we still have about the glassy state, no. Well, these are my people with I work with, mainly Javier Rodriguez Viejo, who is the leader of our group, then other senior colleagues like Marta and Jordi Frasedas, and of course, we have some PhD students who have already, and Avila already finished, who have contributed to this work. This is my email address, so please feel free to contact me in case you have any question or any comment you want to give afterwards. And I will show also some results at the end about low temperature properties, no, which is the main subject of these kind of seminars. And this low temperature, or let's say, regarding to the glassy anomalies, no, we all know, are performed with collaboration of Miguel Ángel Ramos in case of heat capacity and Giacomo Baldi in the case of the measurements of the vibrational density of states. No, in fact, Giacomo Baldi was the previous speaker, so probably you already know many details about that. I have to say that I work with ultrastable glasses. Okay, I'm, let's say, an expert on ultrastable glasses, but not so much about these kind of anomalies. So I will explain what we did, but of course, both Miguel Ángel Ramos and Giacomo Baldi knows much more about these experiments I will show at the end than myself. No. Again, already Maxim said this. I work. I'm, let's say, associate professor at the Universitat Autònoma de Barcelona. I'm also affiliated to the Catalan Institute of Nanoscience and Nanotechnology, and inside this group of thermal properties of nanoscale materials. Okay, and here some acknowledgement of the funding agencies that have allowed this research. So very brief outline of the talk. So first, I will talk about the formation of glasses, no, and their properties, and in particular, how can we overcome the limitations when forming glasses with the methodology of vapor deposition, no, to form ultrastable glasses, and some of the properties they have. Then I will talk about the transformation of these glasses, okay, ultrastable glasses, but also transformation of glasses in general. And at the end, as I said, I will talk about these low temperature anomalies, no, which are well measured by heat capacity with Miguel Ángel, basically PLS level systems and the boson peak, no. Okay, so just to start, as an introduction, you know that typically glass can be formed by cooling a liquid. No, so you are in the liquid state. You start decreasing the temperature. If you are able to surpass the crystallization, no, the crystal would be the thermodynamical favorable phase. But we can overcome this crystallization process if we cool fast enough, and then we enter in the supercooled liquid regime. No, and when we enter in the supercooled liquid regime, here in this plot, you can see that the relaxation time increases very sharply when reducing the temperature. Eventually, the time the system needs to equilibrate to stay in the liquid state, in the supercooled liquid state, is longer than the available experimental time. So at this moment, the system goes out of equilibrium, and then we form a glass. No. If we go faster, so this deviation from equilibrium occurs at higher temperature. If we go slower, we can stay at equilibrium down to lower temperatures. But this, let's say, range of temperatures at which we can stay in equilibrium by cooling at different rates is not significant. So in any case, we will get a glass which deviates very soon from the liquid state at the glass transition temperature, which, you know, it depends on the cooling rate, as I was saying, but you cannot get a broad range of glass transition temperatures by cooling at different rates, okay, because of this abrupt increase in the relaxation time. Here you have already emerges one of the main questions now we have in the glass community, which is whether this glass transition temperature, or this glass transition process, is kinetic, is purely kinetic, or there is some kind of hidden phase transition. Okay, and this is one of the questions we will try to answer, or not answer, of course, but we will try to provide new approaches to try to solve this question. No? So I was saying, this abrupt, this exponential increase in the relaxation time, this is, well, I will not go much into detail, but this is considered to be consequence of this formation of these cooperative rearranging regions, which are clusters of molecules or atoms that relax cooperatively. And because of these cooperative rearranging regions grow larger and larger as the temperature is decreased. So this is why we have this kind of increase in the relaxation time. No? The direct observation of these rearranging regions of these dynamic heterogeneities is quite challenging, because these clusters are very, very small, it's nanometer size. So the observation of this is quite challenging, as I was saying, but again, with the ultrastable glasses, we can provide some new information about that as well, as we will see later in the talk. Now, so this on the left, you see this kind of scheme where we have the bulk of the material, where we have the molecules or the atoms that, as we reduce the temperature, try to relax, try to stay in equilibrium. But since every molecule here is surrounded by many other molecules, so this relaxation process is difficult for them. Every time it's more difficult. But at this year, 2007, Mark Ediger, the group of Mark Ediger, found out this new strategy to form glasses which were more stable, which means that we can a way to prepare glasses, keeping it in equilibrium down to lower temperatures. And this was based on vapor deposition. So instead of cooling down the whole system and trying to keep the whole system in equilibrium, what we can do is to form this same glass, layer by layer by physical vapor deposition. In doing this, if you grow the material layer by layer, the surface molecular layer will have a larger mobility, so it will have the opportunity to equilibrate down to lower temperatures. Okay, we can represent this in this way. So here, the blue line, this is the same relaxation time I was showing before, the bulk relaxation time of the supercooled liquid. At this temperature, the gas transition temperature, the system goes out of equilibrium, typically considered to be 100 seconds. But this This red graph here is just a schematic. It's not a real measurement, but this is a representation of what would be the relaxation time of the surface layer, no? The surface layer of the glass as it grows by physical vapor deposition. You see that the relaxation time of this surface layer, because it is not surrounded by many other molecules, it lies on the surface. The relaxation time is much the relaxation time is much shorter. No, it can equilibrate faster. It can stay in equilibrium faster. Let's say. So we can go to lower temperatures by keeping this surface layer in equilibrium, and therefore we can prepare a glass which is, so you see, lower enthalpy, so more stable glass. Okay, so this is the basic idea under the idea of the ultrastable glass. No, taking advantage of this faster surface mobility. No, the relaxation time has not been measured directly, but for example, the surface diffusion has been measured. Okay, and we see that the surface diffusion in many molecules, in many systems, is way the diffusion is larger, no, which means faster relaxation time as compared to the diffusion in the back, no. So this is the mechanism, no. We take advantage of this faster mobility on the surface to keep the system, the glassy system, or the supercube liquids in equilibrium down to lower temperatures. Again, so this is not the same everywhere, so let me go backwards. Eventually, even this surface relaxation time will be larger than the experimental available relaxation time. No? So if we continue going down and down in temperature, even this new methodology to prepare a glass will fail. No? So will not be able to keep the system in equilibrium down to infinitely low temperatures. No, of course. So if the substrate temperature is too low, very, very cold substrates, then the molecule that gets to the surface will immediately lose the energy, and then we will get again a very unstable glass. Okay, there is a temperature range in which we can optimize this surface mobility and get a more stable glass. Okay, and this is what we get when we grow the system at 85% of the glass transition temperature. Okay, if we grow the glass if we grow this thin layer by physical vapor deposition, which is the glass, at 85% of the glass transition temperature, we will get a glass which has very large stability. No, here we can see some examples. So it was with indomethacin, which was one of the first molecules with which the concept of ultrastable glasses was tested. No, and these are calorimetric measurements. Okay, we see here these small bands. These are the let's say the ordinary glasses, no, the glasses that have been formed by cooling from the liquid. You see at 10 Kelvin per minute or at 0.1 Kelvin per minute. You see the one prepared at 0.1 Kelvin per minute is a little bit the onset temperature, the onset of the multiplication. So when we change from glass here to the liquid is slightly larger in the case of the 0.1 Kelvin per minute cooling rate, but not significantly larger. Okay. On the other hand, if we grow the system, if we grow this glass, this indomethacin glass, at 266 Kelvin, which is exactly 85% of the glass transition temperature of indomethacin, we have this denitrification peak, which takes place at much higher temperature compared to the glass that has been formed by cooling from the liquid. Okay, you see here larger denitrification temperature, and the area under the peak is also larger, which means that the change of enthalpy between the glassy state and the liquid state is also way larger, which means higher thermodynamic stability. Okay, but again, as I was saying before, as we change, this is the deposition temperature. As we change the deposition temperature, in particular, if the deposition temperature is 119 Kelvin, which is very low, then we have again this vitrification peak, which is at a temperature similar to those that we get when we prepare the glass by cooling from the liquid. Okay, so again, if the substrate is very small, if the temperature of the substrate is too low, so then we again have a very unstable glass. Okay, we need the temperature of the substrate to have a proper value in order to be able to get a very stable glass. And this very stable glass can be compared with, for example, amber. Okay, this to have an idea of how stable is this glass. Okay, in amber, we see again here a difference in. This is measured by Michelangelo Ramos, by the way, with amber. We see this change, no, of the rejuvenated amber, which would be like the ordinary glass prepared by cooling from the liquids, and the amber, the original amber, which is a system that has been aged for millions of years, no? So we see a change in onset of the vitrification of 30 Kelvin, which is similar to this. Here we have like 20 Kelvin difference in the vitrification temperature, okay? With this, I want to say that by evaporating at the proper conditions, but with physical vapor deposition, we can get glasses with a similar thermodynamic stability and with a similar kinetic stability than those glasses that has been aged for millions of years, no? Such as this amber. I'm not saying this is exactly the same because there are many differences in many properties, but from the point of view of kinetic and thermodynamic stability, these are very, very similar, okay? Other properties which are also relevant in the field of ultrastable glasses, for example, the density, no? This increased the vitrification temperature is used to increase density, okay? The molecules in the ultrastable glass are like more efficiently packed, no? And therefore the density is higher, which at the same time, this is responsible for the increase in the vitrification temperature. You see here, no? We can reach maximum or approximately maximum densities when we grow the glass at 85% of the glass sufficient temperature. This is what I was saying before, no? The onset temperature of the vitrification as a function of the position temperature. We have here many materials. Nowadays, we have many more materials than this. There are many materials that follow the same trend, okay? The onset of the vitrification when we heat from the glass to the liquid is larger when the glass is deposited, is maximum, in fact, when the glass is deposited around 85% of the glass transition temperature, which is around this value here. And these glasses, which are called ultrastable glasses, in fact, they are called ultrastable glasses because of the larger thermodynamic kinetic stability, but also because when we take this glass and we go above TG, above the glass transition temperature, no, it takes much time to transform back to the metastable equilibrium state, no, to the liquid state. So in fact, there is approximately the same for all materials, 10 to the 4 times larger than the time that the ordinary glass would take to go from the glass to the liquid, no? So we have for a conventional glass, for example, if we go to TG, it's considered that the transformation time, that the relaxation time is 100 seconds, no? In this case, if we take the ultrastable glass, here, again, 85% of the relaxation temperature, we have like almost 10 to the 4 times, okay? So it means that we have to wait for 10 to the 4 multiplied percent per 100, so 10 to the 6 seconds to go from the glass to the liquid at the glass transition temperature, okay? So million seconds, so many thousands of hours, so many days. So 100 seconds for the ordinary glass, 1 million seconds for the ultrastable glass, okay, at the same temperature. Okay. Other properties which are interesting to consider when we look at the ultrastable glasses is related to the secondary relaxations, okay? You know that apart from the structural alpha relaxation process in glasses that are mainly responsible for this formation of the glass and also for the vitrification of the glass, apart from this alpha, we have other more local relaxations, no? such as the beta relaxation, the Johari-Goldstein beta relaxation. Not all beta relaxations are Johari-Goldstein. And then we have other Johari-Goldstein relaxations, okay, which are more partial part of the molecules which relax. Now, what happens with these relaxations in these ultrastable glasses? Well, here, these three materials, there are many, there are more, okay, but we have some example of this toluene, ethylene, semi-tartan, which are materials that exhibit this Johari-Goldstein relaxation, no? So if we measure this Johari-Goldstein relaxation in these systems, we see that they are slower, okay? They are slower, and they are slower in a way that if we measure the beta relaxation time at the glass transition temperature at the onset of the vitrification, we see a shift which is similar to the shift we observed when we measure the vitrification temperature, okay? So, well, this is to say that this Johari-Goldstein relaxation in these materials behave in a similar way, are sometimes, let's say they are like linked with the alpha relaxation, okay? If the alpha relaxation is slower, the beta relaxation is slower in a similar way, okay? On the other hand, we have other materials which exhibit other kind of relaxation, which are non-Johari-Goldstein, and in that case, what we see in the ultrastable state is that they are not slower, but they are faster, okay? So they are not linked with the structural relaxation of the system, okay? So this is a way of this is a property of the Johari-Goldstein beta relaxation, no? So we can clearly distinguish which relaxations are Johari-Goldstein because they are linked with the alpha relaxation, and we can compare to those relaxations which are non-Johari-Goldsteins, which are not linked with the alpha relaxation, okay? This is giving some extra information about the secondary relaxations, okay, which is, you know, is also a field of debate, no? There are other things that I could explain about that, but I will not go in much into detail about that. Let me explain other properties of ultrastable, of vapor deposited glasses, okay, which is very important in this case. You know, ordinary glasses are isotropic, okay. Let's say by definition, no, one would expect that the glass is completely isotropic, but when we grow the material by the glass by physical vapor deposition, we can get some kind of anisotropic packing. Okay, this is just a scheme. Okay, this is not the real scenario. This would be a crystal. An ultrastable glass is not that perfectly aligned, but it's way more oriented. It has some degree of anisotropic packing. Okay, which depends on the deposition conditions. Okay, and this has been verified with, for example, with we will see now. This is verified, for example, by X-ray diffraction. No, here I have some plots at the afterwards, which you will see. So this is the idea, no? If this degree of orientation can be parameterized with this parameter S subset, okay, which is just a way of measuring the angle, no? The degree of orientation, the angle with respect to the substrate, no? So if this parameter S is equal to 1, it would mean that all the molecules are perfectly aligned in this direction, perpendicular to the substrate. On the other hand, if this parameter is minus 0.5, it would mean a perfectly orientation parallel to the substrate, okay? And 0 would be completely isotropic. And this is what we have experimentally, no? With, for example, TPD, an organic molecule typically studied. See, 0 when we deposit the glass above Tg or at Tg as expected. Here we have an ordinary glass, 0 orientation parameter completely isotropic. But if the substrate temperature is decreased, then we enter in a regime where the molecules are slightly oriented in this way, with the molecules perpendicular to the substrate. Okay, this is not, you see, the magnitude of this parameter is not 1 here, it's 0.15, for example. It means that they are not like this, but they are slightly oriented in that direction. Now, we can continue decreasing the substrate temperature. If we deposit the glass at 0.9 approximately, we again have an isotropic glass, okay? S equal to 0, which means completely random. And then if we decrease the temperature, we enter in a regime at low temperatures, at low deposition temperatures, where the S parameter is like 0. Minus 0.35 approximately, which again means that the molecules are not perfectly aligned parallel to the substrate, but there is a significant degree of orientation in that direction, okay? And this is very important for many properties, as we will see afterwards, okay? Again, this is the same. This is the experimental points for different materials. This can be measured, as I was saying, with X-ray diffraction. You see here, you see this typical amorphous halo of glasses, no? The distribution of intensity along this halo is not perfectly uniform, as one would expect from a completely isotropic system, but especially in this case, substrate 260, which is low temperature, below 85% of the oxygen temperature of the material, which is CPD. We see here a strong accumulation of intensity here, which means that the molecules are, in average, are oriented in this way, okay? Perpendicular, parallel, sorry, to the substrate, okay? Not perfectly parallel to the substrate, but a significant degree of orientation across this direction. If we now increase the temperature, 315, below the TG, but not much below, we see certain accumulation of intensity here in this direction, which means the molecules are significantly oriented in this direction, okay? Perpendicular to the substrate, okay? Okay. As I was saying, it has a strong impact on many properties, mainly transport properties, charge transport properties, okay? The mobility in different directions is different depending on the orientation of the molecules. Also, this is not depicted here, but thermal transport is also affected, okay? There is a publication in our group, in fact, where they measure the thermal conductivity, and it changes in this direction and in this direction, okay? So this physical vapor deposition offers also a way to control also thermal transport, okay, which can have many applications in many cases. Okay, another important property, another important consequence of this molecular orientation is that now, if we take molecules with a dipolar moment, okay, PPD has not very strong dipolar moment, less than 1 dBi. But in any case, you can see, that if you align the molecules in this way, and each of these molecules has a dipolar moment, and the molecules orient in a way that the positive pole of each molecule goes in the same direction everywhere, always. So they are not cancelled. They are not completely cancelled in all the cases. You can get a thin film where you have a very large effective dipolar moment. No, so you sum all the molecules, all the dipolar moments in all the molecules, and at the end you end up with a thin film which can exhibit this the giant surface potential. No, so to generate a differential potential difference between one side of the film and the other side of the film that can be like even 100 millivolts per nanometer, okay? So at the end, if you grow a layer of 100 nanometers, for example, which is a typical size of molecule of layers of films in electronic applications, for example, you can end up with a thin film that spontaneously generates a voltage difference of many volts, okay, from one side to the other of the film. And this can have many applications, okay? You can also play with the polarization, okay? When you change from the glassy state to the liquid state, and if in the glassy state you have this kind of giant surface potential, when you convert the system into a liquid, you generate a current pulse because of this depolarization, okay? And this can be used, for example, in neuromorphic applications, okay, which is something that we are now starting to explore in our group. Okay, so far everything I wanted to say about the properties of the ultrastable glasses. Let's now change to see how these glasses transform from glass state to the liquid state when we go above the glass transition temperature. Okay, so imagine you take a ordinary glass. Okay, this glass that you have formed by cooling from the liquid. Okay, you take a liquid, you cool it down, you form a conventional glass, and then you go with this glass above the glass transition temperature. And what you can observe is that the system converts into the liquid state in a, let's say, via a bulk mechanism. No? So the whole bulk of the material, the whole film, the whole glass goes into the liquid. Okay, let's say simultaneously, the whole volume simultaneously goes into the liquid state. Now, what happens if we do the same with a ultrastable glass? Okay, this glass that we have grown at 85% of the TG of the material, which is higher, which has a higher density, larger devitrification temperature, and so on. Now we go above the devitrification temperature. The density of this material is so large, the mobility of this material in the bulk is so small because of these efficiently packed molecules that on the surface, the mobility is higher. So on the surface, the transformation will start sooner, okay? So the same higher mobility that allowed us to prepare the ultrastable glass because the mobility on the surface was higher. Now, this higher mobility on the surface is producing that the glass will start to transform back into the liquid state from the surface, okay? Mainly from the surface or also from the substrate, no? Depending on the interaction that is between the glass and the substrate, okay? If there is no very large interaction, we can also observe some transformation from the interface with the substrate, okay? But in general, the transformation starts from the surface. Okay, so we form a liquid layer on the surface, and then this liquid layer on the surface will propagate into the bulk, okay, as you see here. So first you form a very thin layer, and then this thin layer will go towards the bulk of the material at a given velocity, okay? And then we'll show some experimental results about that. What I want to say is that this front, so the layer starts here on the surface, no, the liquid layer, it propagates into the bulk, but eventually the bulk of the system will go into the liquid state as well, okay? After some time, the mobility of the bulk has had some time, and then it will transform into the liquid state. So we can define a crossover length, which is the distance that this liquid front can travel before the bulk transformation dominates. Okay, so this is the crossover length. Now, imagine that we want to study the bulk transformation of ultrastable glass. Okay, in fact, this is what we want to do, not to study the bulk transformation. We are not interested in surface effects. We want to study the bulk transformation. So we have two strategies. One is taking advantage of this, no? So instead of growing 100 nanometers, we grow 1 micrometer or 10 micrometers. So in that case, of course, the transformation will start from the surface, but since it has to travel a very large distance, eventually the bulk transformation will dominate. Okay, so let's say that if the film is thick enough, we can neglect the effects of the front transformation. Okay, this is one strategy. There is another strategy which is more intelligent, let's say, which is capping the surface. Okay, so imagine this is the glass we want to study, TPD, which has a glass transition temperature of 333 Kelvin. Okay, you have it here. We go above this temperature to study the vitrification of this TPD. but we see that on the surface, the transformation will start earlier, no? So what can we do? We put on top of this TPD, we put another material with a higher TG, okay? Let's say we go to 340 Kelvin, for example, if we want to study how the TPD will transform. At 340, you see the TG of the TCTA is 424. At 340 Kelvin, the TCTA is still in the glassy state, okay? Very deep in the glassy state. The mobility in the TCTA is very low because it's in the glassy state. So this low mobility we have here in this interface, also here, will avoid the front transformation, okay? Will avoid the relaxation on the interface of the TPD with the TCTA. Okay, so this is a way of avoiding this front transformation, okay? Okay, so I will show again, as I was saying before, I will show experimental results on that. So how do we characterize this? So this is a scheme of the evaporation chamber, okay? So we have here let's say the evaporation source. On top can be different configurations. We have here the material evaporating, and here we have the substrate where we study this process, this liquefaction process. So here on this substrate where the material will deposit, we put our colorimetric cell. Okay, how is this colorimetric cell we use to characterize this transformation? This is this kind of device, okay, which is a nanocalorimetry cell. Okay, this is a technique which is called fast scanning nanocalorimetry. Okay, this is just a very small device. Okay, this is like 1 centimeter square more or less. Here in the central part, here we have a freestanding membrane, okay, of silicon nitride. So this is 180 nanometers silicon membrane. And on top of this membrane, we have this metallic element, which is 100 nanometers platinum film. Okay, so what we do here, we grow the sample, the glass, on this central area, okay? And then we inject a current pulse, as you see here. Okay, this is the intensity pulse we inject through this path here. This is a very short pulse, milliseconds in time, milliamperes in intensity. But since the addenda, so the heat capacity of this device is very slow, it can heat up very fast, even with this small amount of power. Okay. It heats up very small, very fast. Fast, it means like 10 to the 4, 10 to the 5 Kelvin per second, okay? Typically, we work at this heating rate, 55,000 Kelvin per second, okay? So very fast. So fast that we can consider this measurement as quasi-adiabatic, okay? Quasi-adiabatic, why? Because we don't have losses, temperature or power losses by convection, because remember, we work in vacuum, ultra high vacuum. We don't have losses by conduction because we are injecting the power so fast that there is no time for thermal diffusion to bring this heat into the frame of the device, okay? So there is no losses by conduction as well because we are heating very fast. And also there are no losses by radiation because we typically work in a temperature range where radiation losses are negligible, okay? We are, remember, the glass transition temperature is 330, 350 Kelvin, so very close to the ambient temperature, so no radiation, no losses by radiation, okay? So this is a adiabatic measurement, okay? Quasi-adiabatic measurement. And then we can calculate the heat capacity. We work in differential mode. There is a complex equation here, but basically this is okay. The power we inject divided by the heating rate. Okay, the beta is the heating rate. And in that way, we can measure the heat capacity during the transformation from glass to liquids in very thin films. Okay, this is the important thing here. We can measure the heat capacity and the transformation dynamics of very thin films. Okay, 10 nanometers is more than enough to study the vitrification process. And this you see here is typical colorimetric trace. Okay, you see this is the glass. We enter in the vitrification window, let's say. This is the onset of the vitrification. We have this jump, which is due to the excess of enthalpy. And then once it is transformed, we measure the heat capacity of the liquid, okay? Glass, liquid, and transformation. This heat capacity can be modeled with this equation, okay? So basically we have the contribution from the glassy state, the contribution from the liquid state, and the contribution of the excess enthalpy, no, the change of enthalpy between the glass and the liquid, okay, which depends on the temperature. So these are basically the two parts, no? This one on the right, the heat capacity of the gas and heat capacity of the liquid, plus this contribution here, which is from the enthalpy of the vitrification. So this plus this is basically the experimental measure. Okay. This is typically when we have bulk transformation. So remember, conventional glass that transforms into the liquid via bulk mechanism. Okay, the whole volume transforms simultaneously into the liquid. What one typically do is just take this heat capacity, this experimental heat capacity, and divide it by the mass. Okay, and you have the specific heat. Okay, but if we have a glass which is transforming, as I was mentioning before, which is transforming via front, starting on the surface and propagating into the bulk, we can not normalize the heat capacity with the mass. Okay, why? Because the whole mass is not involved in the transformation process. Okay, only a layer which is initially very small, and then it propagates into the bulk. Okay, this is the only part which is contributing to the vitrification, not the whole mass. So what we have to do here is to use another normalization protocol to understand the transformation mechanism. Okay, we can do this to assuming that transformation takes place via this front that starts from the surface and propagates into the bulk. We can change. Basically, we change the transform fraction we had in this original expression. The x is the transform fraction. We can change this transform fraction with this d, which is the thickness, which is the thickness of the liquid part that has been transformed into the liquid. Okay, the liquid thickness, let's say, which depends on temperature, okay, and time, of course, but temperature here because the temperature is depending on the time. And then when we do this, what we can do to normalize this is to keep in one side of the equation all the parameters which are not dependent, which does not depend on the particular sample we are measuring, okay? So which means the thickness of this liquid layer, which does not depend on the sample, does not depend on the thickness of the sample, which is only a property of the temperature, and well, these parameters which are properties of the material, okay? The specific heat of the liquid, the specific heat of the glass, and enthalpy of transformation, okay? Let's put this into practice, okay? So here we have a fast cool glass, okay? So this is a conventional glass, let's say, cooled from the liquid very fast, but still a conventional glass, okay? This is the specific heat. So this has been obtained by measuring different thicknesses, you see here, from 100 nanometers to 15 nanometers, and dividing by the mass. And all the curves collapse into a single curve, okay? So the specific heat of all the samples is the same, as we would expect, no? Because this is the same material, so specific heat should be the same regardless of the thickness. Now, we do the same for ultrastable glass. Okay? We said before, ultrastable glass does not, or this is at least at this moment, this is the hypothesis. No, we are working with ultrastable glasses do not transform via bulk mechanism, but front transformation, starting from the surface, propagating into the bulk. Okay, so if we now normalize by dividing by the mass, as we did here, we get this. One would say, okay, so the glass, the vitrification temperature depends on the thickness, but it's not, if the mechanism of transformation is the one we said, this is not right. This is not true because we are normalizing by the mass. So the mass is involved in the transformation process. It's not the same in all the samples. Okay, let's say the percentage of the mass involved in the transformation process is not the same in all samples. So if we want to really extract a conclusion about this transformation, we have to use this other normalization protocol we established before. Okay, so this is dividing by the mass. This is now normalizing in this way, okay, assuming that this front propagation. So we see all the calorimetric traces, all the calorimetric curves collapse into a single one during the vitrification. So it means that indeed the transformation is proceeding in this way. Okay, this is a front which is traveling into the bulk at a given velocity. Okay, of course, for the 20 nanometer thickness film, this front will travel until it consumes the whole glass, and when it consumes the whole glass, the heat capacity goes to 0 because there is nothing else to transform. Okay, if the sample is 110 nanometers, the front can travel a longer distance until the whole glass has been consumed. Okay, and then again back to not 0 but low value. Okay, so this is the front propagating into the bulk. Okay. Of course, this is the other verification. No, so this is for the ultrastable glass. This is for the fast cool liquid. Okay, conventional glass. If in a conventional glass we apply the same normalization process, which shouldn't work, okay, because we said fast cool glass prepared by quenching from the liquid state, it transforms via bulk process. So now it doesn't work because this is not transforming via front propagation. Okay, so this is bulk mechanism. Okay, so everything works here, and in fact, from here, from this calorimetric curve, we can obtain this growth front velocity. Okay, with this term here, the variation of thickness of the liquid phase as a function of temperature can be related to the growth front velocity. Okay, the velocity of this front that travels into the bulk with this expression, and this is what we get with calorimetry, with conventional DSC, and with other techniques. And this is the relationship we get when we plot this against the relaxation time of the liquid. Okay, this tau is the relaxation time of the superheated liquid, and it follows this relationship here, which is empirical, and which works with this exponent here, which should be negative. There's a mistake. This exponent here is quite similar in different systems. Okay. Okay, so I will go a little bit faster because of time. But basically, important thing here is that this can also be this protocol can be also be applied to a glass, which is vapor deposited as well, but it's not that stable as the ultrastable glass. It is deposited at 310 Kelvin, so not the ordinary glass, but also not the ultrastable glass. We do this normalization, and we see here some region where these curves collapse in a single curve. Okay, so this in the ultrastable glass, it was happening up to larger temperature. Here, only in this region, in the fast cool glass, nothing. Okay, so it means that here we still have some degree of transformation that takes place via front propagation. Okay. And what about the velocity of propagation in this case? Okay, so here we plot this velocity of propagation as a function of the relaxation time of the superheated liquid. and we see some change depending on the stability of the glass. Okay, this is the more stable glass, so the velocity is lower at a given for a given temperature. In the case of the less stable glass, this front propagates at a larger velocity. Okay, so what it means? So this is the expression we saw before: alpha relaxation time to a power of around 0.8. But also we have here this prefactor here, this C, which depends on the stability of the glass. Okay, so this is not only the liquid which is governing transformation, but we also have some influence of the glass matrix. Okay, and it can be understood in this way. No, so this is the glass matrix, very well packed in the ultrastable glass. This is the liquid, which is already loosely packed, and here in between we have some region with, let's say, which is seeing the liquid on one hand and the glass on the other side. So we can consider that the time this intermediate region has to transform into the liquid state is some kind of geometrical average between some kind of transformation time of the glass and the relaxation time of the liquid. Okay, and if we do this, we have seen that it quite can be used to obtain this growth from velocity. Okay, so summarizing, this means that the growth from velocity comes from here. Okay, so it comes from the fact that this intermediate region, this interface between liquid and glass, is governed by a time scale from the glass here and a time scale from the liquid. Okay. Now we said if we want to avoid this glass, this front transformation, we can just cap the surface, the interfaces. Okay, we freeze the surface, so we eliminate this higher mobility on the surface from the equation. Now we have only the bulk, so only the glass can only transform via bulk process. Okay, how can we know that we are effectively suppressing this front transformation? So we can measure. This is TPV, okay, capped with this uncapped, so the one we saw before, normalizing by the mass, and we see this apparent size effect, which is, as I was saying, it's not a size effect. This is a consequence of front transformation. If we now do the same, but capping this glass that we want to study with a higher TG material, so TPV capped with TCTA, we have this devitrification temperature for samples of different thicknesses. Okay, so you see 20 nanometers, 40 nanometers, 75 nanometers, all of them have the same devitrification temperature regardless of the thickness, which means that indeed, in this case, when the glass is capped with higher TG glass, then we have a bulk transformation. Okay, and this is how we can access bulk transformation properties. Now we study this process. So we have our glass that we deposit at a given temperature. So if we want the ultrastable state, we grow it at 85% of the glass temperature. Then we go above TG, so at a temperature at which we want to study the transformation process. It has to be above TG, of course. And we do an isotherm at this temperature, okay? And we choose a time, okay? So 1 hour at this temperature. And then we cool the system down at the glassy state. And now, what the thing is that the question that we want to answer with this experiment is what has happened to the glass during this isotherm. Okay? If some liquid has appeared here, if some part of the material has transformed during this isotherm, and then we have cooled it down, then what we have is that these regions that have become a liquid during this isotherm, now there should be a fast cool glass. Okay, so they should be now conventional glass. So how do we know if we have conventional glass? So we perform a calorimetric measurement. Okay, and this is what we have. Okay, so this is the initial state as deposited glass. Nothing, no isotherm for the moment. 0 seconds isotherm. We now submit it to, here we say 347 Kelvin, so above TG. For some time, we see a shift in the vitrification onset. Okay, so something has changed, but we don't see traces of liquid, because if some liquid has appeared, the derivatization should be here around 380 Kelvin. Okay. So for the moment, we see that the glass has changed a little bit, but no liquid has been formed. If we, instead of 30 minutes, now we have now 180, 1 hour and a half, still more change in the glass, but no traces of liquid. Now, 3 hours. At 3 hours, we see a change in the glass peak, in the glassy peak, but we see here some amount of fast cool glass. Okay, so it means that some regions of the glass during this annealing has transformed into the liquid state, and when we perform the measurement, this is manifested via this derivatization peak of the fast cool glass. Okay, so we have some fast cool glass, and we have some still glass that has been changed with respect to the initial glass, but still a glass. Okay, glass that has not become a liquid during this process. And this process continues until eventually the whole system is a fast cool glass. Okay, so everything has become a liquid at this temperature. Okay, so this is the full process. Okay, we see this relaxation of the glass, which we call softening, and we have this emergence of the fast cool glass, which is related to the emergence of this liquid phase in the glass. Okay. And this is how it looks like for different stabilities. Okay, this is fitted with an Abrami, which it is not perfect fit, but just to have an idea. For the most stable glass, we have this black point here. You see here, we have to wait for almost 10 to the 4 seconds before we start seeing some fast cool glass, okay? Which means before some liquid appears in the glass, okay? And then once it appears, then the amount of liquid increases until everything is already being transformed, okay? And this is for different glasses, different stabilities. The lower the stability, this is more closer to the glass oxidation temperature of the TPD. The smaller is this annealing time required to become a liquid. And also, this is the position of this peak. This is also relaxing. I will not go into detail about that. This is important. We observed something similar also in the ordinary glass. Okay, if we age the ordinary glass, if we prepare a glass by cooling from the liquid and we age the glass to increase the stability a little bit, and depending on the annealing temperature, we can see either only this change in the glass before observing the liquid, or if the temperature is larger, we can see the emergence of these liquid regions. Okay, so depending on the annealing temperature, we see one process of equilibration into the final state, or another mechanism. Okay, again, not many details about that, but this is also an interesting observation. Now, this is another way of characterizing this transformation. Okay? Instead of calorimetry, where we have indirect access to these liquid regions, we can just measure with AFM. Okay, in this case, so what we do here is we take this system, PD, the system we are studying, capped with PA. Okay, what we do is, again, basically bring it to this annealing temperature, okay, above glass solution temperature, and we see how this surface evolved with time, okay, during this isotherm. Okay, so we measure with AFM the topography of this capping layer during the isotherm. Okay, and this is what we get. Very interesting. So at the beginning, so initially we have a completely flat surface, but eventually we observe the emergence of some bumps. Okay, when time goes on, we see more and more bumps which then start to grow laterally until everything, all the sample is completely filled with this kind of structures. Okay, so completely corrugated. Okay, the interpretation we do, which is compatible with what we said with calorimetry, is this. We start forming these regions which has become a liquid, which then they grow. When they grow, they reach this capping layer, and when they reach this capping layer, remember that the liquid has higher density than the glass, so it pushes this capping layer, and this is what we see here, okay? And once it grows in this direction, it cannot grow larger because this is the thickness of the film, but eventually it will grow laterally, okay? And when it grows laterally, we have these kind of patterns which is produced due to the release of stress of this capping layer, okay? This is a mechanical effect, basically, and it goes laterally until the whole sample is transformed. Okay? So again, this again a quite direct evidence that the system is transforming via bulk, but via bulk heterogeneously. Let's say some regions become liquid before other regions. Okay. Well, this is a comparison of AFM transformation with calorimetry. Well, this is compatible, so nothing interesting here. What is interesting is what we get from here. So here we plot the number of liquid regions. Okay, this kind of protuberances we observe in the capping layer as a function of time. Okay, we have this and per unit area. We have this kind of plot, and from here, from this slope here, we have the nucleation, let's say, frequency, no? So if we do the inverse of this and we linearize, we get that for a unit of time, we have the emergence of these bumps at separated distances of 130 micrometers. Okay, so the distance between one region transforming into the liquid and other region transforming into the liquid at the same time is 130 micrometers. Okay, so what does it mean? It means that two regions with the same relaxation time, okay, because they have transformed into the liquid at the same time, they are separated 130 micrometers of distance, no, which is giving us an idea of some kind of dynamic length scale, okay, which is very large in the case of this ultra-stable glass, okay? If we do a less stable glass, instead of 85%, we do 90% of the glass layer temperature, then this number is not 130 micrometers, it's just 13 micrometers, okay? So this liquid bumps appears much close to each other, which means that this dynamic heterogeneity length scale is much shorter. Okay, if we continue doing this, if we would continue doing this, we would reach the stability of a conventional glass, where we would expect that this distance, this dynamic heterogeneity distance, would be of the order of nanometers. Okay, so it matches quite well with the expectations. Okay, this is about this induction time, the time we need to observe the emergence of this liquid as a function of the annealing temperature, which has an activation energy which matches quite well the activation energy of the alpha process at this temperature, which means that this is a structural relaxation process. Okay. Okay, let me skip this part. Okay, so this is kind of a scheme of what I was saying before. Okay, initially we have a distribution, this is the glass, let's say. We have a distribution of relaxation time, all of them being very large, okay, because we have a very stable glass. But each of these regions evolve when we do an annealing, evolve at a different pace, okay? Some regions are faster than the others, and these faster regions become liquid sooner than the others, okay? And these two regions that become liquid at the same time are separated a distance, which is 130 micrometers in the case of the most stable glass, okay? Which is this kind of dynamic heterogeneity. And then if you continue doing this annealing, more and more regions will become a liquid, and eventually the whole system is transforming into the liquid. Okay, so this is the important thing that we can observe with ultrastable glasses. Okay, that we somehow can be able to measure kind of dynamic correlation length. It's not exactly a dynamic correlation length we have in the respective liquids, but it gives us some idea of the separation between the distances that has similar relaxation times in the glass, okay? Okay, and with this, let me already talk about low temperature properties, okay? So these are heat capacity measurements performed by Miguel Ángel Ramos, okay, in the Autonomous University of Madrid. This is indometacin, okay? Remember this prototypical molecule that we used started to use when we were started to study the ultrastable glasses. Here you see the crystal, okay? So typical heat. This is the heat capacity divided by to the cube, okay? Typical representation to measure to observe TLS and boson peak. This is a conventional glass. The blue points are conventional glasses, okay? So typical behavior of a system with TLS, okay? Typical behavior of an amorphous system. But here, these purple points and also these ones are two ultrastable glasses. Okay, we have here that we observe here that we don't have any signature of TLS. Okay, this is one of the. It was a striking observation. Okay, so in the case of the ultrastable glass, we observe absence of level systems. Okay, so this anomaly, which is universal of glasses, is not observed in the ultrastable glass. Okay. Now, if here we have this degraded USG, this means that this is a USG after some time, after which the glass has absorbed some water. Okay, so when the system was degraded, so some water inside, then we already observed again these two level systems. Okay, same as in conventional glass. Okay. At this point, we concluded that this elimination of the two-level system was due not to the density, but to the stability, but to some kind of anisotropy. Okay, remember, we have this anisotropy in the case of the ultrastable glass. Okay, and then. So, well, the conclusion the argument we said, it was we have some kind of requirement of cooperativity between different TLS, okay, that was removed in the case of the ultrastable glass because of this layering. This layering was somehow acting as a breaking of this cooperation between two-level systems. When we add water into the system, for this degradation, we can recover again this network of TLS, and that's why we change from no having TLS to having TLS. Okay. Also, there was this comparison between this amber that Miguel Ángel also measured, the amber, the hyper-aged glass, okay, a glass naturally aged for millions of years, with this PVD glass, okay, this ultrastable glass prepared by physical vapor deposition that exhibits a similar thermodynamic stability, okay, but by very different routes, okay. So in the case of the amber, so this is the amber. Again, we still keep this TLS, okay. Even being more stable, we still observe this TLS, okay. That's why we concluded that the disappearance of the TLS was not due to the density, to the stability, but to the anisotropy, okay. We studied a different system, okay, TPD, again TPD, okay, you know it already. Now, you know, we can tune the orientation of the molecules, okay, if you grow the molecule at 85%, so the most stable glass, which is this one here, larger onset of the vitrification, we have some degree of orientation, okay? Order parameter negative, it means molecules slightly oriented in this direction. But if we grow the material at 90% of the TG of the material, you see we are very close to the isotropic state, okay? S equal to 0 or practically equal to 0, while still having a huge stability, okay? You see the distance between the vapor, the positive glass, And the ordinary glass, the conventional glass, is very high, very large. Okay, so still we have a very stable glass. Okay, but in one case, this is there is some kind of anisotropy. Here, this is in principle completely isotropic. And what can we see when we do the same? So we see that there is a lack or a strong reduction, let's say, of TLS in both systems, okay? Even in the isotropic ultrastable glass, S equal to 0, remember, so no orientation, we still have a practically 0 amount of TLS compared to the conventional glass, okay? You see here? So what does it mean? It means that indeed the disappearance of TLS is not due to the orientation of the glass, but it has to be due to the density of the glass. Okay, so then, well, these are different representations. Then what happens with the amber? Okay, remember that here we have this amber where we have this TLS even being very stable. So one possibility is that the amber has aged not because the stability has been increased, not because the molecules are more densely packed, but because of some kind of cross-linking, okay? So some kind of cross-linking has taken place during this long time of aging, and this is now something, this is not a glass which is much stable, but this is a different glass, okay? So this is different. In the case of the ultrastable glass, we really have the same structure, but more densely packed, okay? So this could be an explanation of why we observe a disappearance of TLS in the case of the ultrastable glass because of the stability, while in the case of amber, we still see the TLS as in the rejuvenated amber, okay? Okay, so, well, I also have something here about the experiments performed by Giacomo Baldi, but, well, the conclusions are basically well, you saw, I don't know if you were present here in the talk by Giacomo Baldi last in the last seminar, but the conclusion was basically that in the case of the ultrastable glass, we observed a reduction in the bottom peak by a factor of 2 with respect to the Debye level, which was something here, okay, and which in this case, we only studied the ultrastable glass, so in principle, we concluded that the reason for this decrease was the density, the increased density of the system, but strictly speaking, we cannot discard the role of anisotropy here, okay? So I will not say much about this. As I said, Giacomo Baldi was here last seminar, so I will leave it here with this summary of everything I was explaining to you. Yes, so I will be happy to answer to any question you may have. Thank you very much for your attention.
Thank you very much, Dr. Rodriguez-Tinoco, for this talk. And now it's time for questions. Dear participants, if you'd like to ask questions, you can act in some way. So you can write your questions in the chat, or you can unmute yourself and ask questions by voice. And I see that Professor Krivchikov is ready to continue.
Thank you very much for your report. I knew information about this system because I hear reports from your group on some discussing, but of course it's I have only small question. You speak about anisotropy.
Yes.
Isotropy and isotropy. And you usually used the anisotropy molecules, like planar or near-planar molecules. And mean you use the terminology anisotropy like geometrical anisotropy of molecules, opaque, yes. But sometimes appear another anisotropy, it like force anisotropy. It means exists different forces in different direction, and a good example of force anisotropy, strong force anisotropy, it's carbon materials. And carbon materials similar have thermal property like case ultrastable glasses in case in the metazine. And this case, you observe different behavioral without boson peak or small boson peak. At what reason? It's connected with force anisotropy or something else?
I couldn't reply to your question because as far as I know, I said before, I'm not an expert on this boson peak, but I wouldn't conclude this is due to the density or to the anisotropy or to force anisotropy. Or I think we need more experiments to say something about that. For example, using let's say spherical molecules. No, there are ultrastable glasses made out of spherical molecules. So we can have, we know it already, we can have ultrastable glasses without any kind of anisotropy, no? I mean, I wouldn't expect any, also not force anisotropy or mechanical anisotropy in this case. So I think we would need experiments on boson peak or TLS on this kind of systems, on ultrastable glasses, okay, to be sure about the role of molecular orientation, anisotropy, or if this is purely due to a change in density. Okay, so I wouldn't dare to give another answer to your question.
Okay, thank you.
You're welcome.
Thank you.
So, another questions? So, I also have a couple of questions. First of all, slide 13.
13? 1-3 or?
1-3, yes.
Okay, here.
Okay. Can you explain more detail the difference between alpha and beta relaxations? So it's, as I understand, the common mechanisms for original glasses and ultrastable glasses. Yes, but what the difference? Why we need two types of relaxation, alpha and beta, and comparison different kind of glasses? What this parameter dominated alpha or beta in original glasses and in ultrastable glasses?
Well, the alpha relaxation in principle is said to be a cooperative relaxation. No, it's a relaxation that involves many molecules. Okay, how they relax cooperatively. Okay, you cannot have an alpha relaxation of a single molecule, for example. This is how the system cooperatively relax from the non-equilibrium state to the equilibrium state. Okay, so it's directly related to the devitrification. No, so when you change from the glass to the liquid, that's because the alpha relaxation has been activated, no? But then we have other relaxations, so like beta relaxation, no? So the beta relaxation is like a movement or a partial movement of individual molecules. Okay, so even in the glassy state, So when you don't have any kind of cooperative relaxation where the molecules can move individually and independently from the others, you can have movement of the molecules, okay? You can have rotation of the molecule, or you can have movement of some parts of the molecule, okay? So if you have, there's a huge debate also on this kind of relaxation. So I cannot say 100% sure what kind of movement is related to each kind of molecular relaxation, but it's considered that if the beta relaxation is more related to movements of the whole molecule, and other secondary relaxations, so beyond beta relaxations, for example, gamma relaxation, other secondary relaxations are more involved, are more related to movements of parts of the molecule, okay? There is another classification, no, which is between Johari-Goldstein beta relaxation and non-Johari-Goldstein beta relaxation, okay? So a Johari-Goldstein beta relaxation is, according to some authors, a relaxation which is directly related, or this is like a precursor of the alpha relaxation, okay? So initially we have the Johari-Goldstein beta relaxation, and this kind of relaxation, this kind of individual molecule relaxation, after some time induces the alpha relaxation, okay? So this is a kind of strong link between this beta and this alpha relaxation. So what we see in the ultrastable glass is that this Johari-Goldstein beta relaxation, which we can measure in the glass, okay? We don't need to go to the liquid to measure them. So these relaxations are slower in the ultrastable glass with respect to the ordinary glass, okay? And it makes sense, no? Because if you have a denser system, it makes sense that the molecules are more slower in their movements, no? So that's why this kind of relaxation is slower. Now, if you go to other kind of relaxations, then in that case, like the ones we have in these maltose or carvedilol or these selecocrypt, these secondary relaxations are faster, no? This is quite striking, no? So if the glass is denser, how can they be faster, no? So this is, I don't have an answer for this, but what I considered the conclusion, the hypothesis, let's say, I provided, is that these relaxations are not coming from let's say, are coming from some kind of, let's say that the glass is formed by clusters of molecules, and in between these clusters, we have some kind of regions that can be, which can have higher density, no? In the case of the ultrastable glass. So it's somehow related to some kind also of dynamical heterogeneity in the glass, no? So the thing is that we can use this difference in behavior between one kind of relaxation and the other, to know the nature of the particular relaxation process, okay? If the relaxation is slower in the ultrastable glass, then we know that this relaxation is linked with the alpha relaxation, okay? If not, we can say that this is not linked to the alpha relaxation, okay? In the following this philosophy of Johari-Goldstein and non-Johari-Goldstein relaxation, okay? Which is a strong debate currently.
Okay, and as I see from the slide, it's also strongly depend on the type of molecules. So in some case, better relaxations faster. In another case, alpha. So here, ultra-stable glasses on the first figure above, original glasses below. And
exactly
in the lower, the opposite situations. Okay.
So this is how I consider this as a way to classify the relaxation, no? Whether this is faster or slower in the ultrastable glass.
Okay, thank you. The next slide, 15. Okay, yes. This order parameter. I see the equations that depend of theta. So what means theta here, and how we can estimate this parameter for the structures from which experiments and in which way?
Yes, so the theta here is the, let's say, this is an average number, so the cosinus is an average between different angles, no? But the theta is, I'm not 100% sure, but this is one thing or the other. This is the angle of the main axis of the molecule with respect to the substrate.
Okay. So,
Okay.
I think in the next slide you was here presented from X-ray experiment, or what type experiment you used for these measurements? How you obtain this angle?
Yeah, it can be obtained from different experiments. No, depending on the experiments, you do it in one way or the other. Here, for example, with X-ray diffraction, in 3D X-ray diffraction, you have somehow to consider this distribution of intensity in the amorphous halo. Okay, so if you have more intensity here than here, so this gives a different number as a S parameter. It's a completely different equation, but just an idea. You have to consider this intensity, as a function of the of this position in the amorphous halo. Okay, so somehow you quantify how much is the concentration of intensity in one direction or in the other. Okay.
Okay. Yes. Thank you. Next.
This is for the X-ray diffraction, but you can also calculate this S parameter, for example, with ellipsometry. Okay, in ellipsometry, you can measure the index of refraction in one direction, in the in-plane direction, or in the out-of-plane direction. Okay, and by calculating the ratio between these two index of refraction, you can extract this S parameter. Okay.
Okay. Yes. Thank
you can imagine that this is information about that. Also absorption and many other techniques.
Okay. Slide 26. What about the speed of cooling? Fast, cooled from liquid, and ultrastable gases. Compare the value of how obtain these gases.
Well, we typically grow the glass, by physical vapor deposition on the chip, and we have this ultrastable glass, So we measure. Look, imagine we have this 100 nanometers thickness. So the black point. We are here. We measure, very fast measurement. Look, we reach the temperature 420. No, so at 120.
I think about obtaining fast cooled from liquid. You have some rate of cooling, so probably 500 Kelvin per second. Yes.
Exactly.
Okay, and what about ultrastable glasses? This parameter?
Well, I mean, you could somehow estimate an equivalent cooling rate, but which would be very, very slow. I don't have the number 10 to the minus 4 or something like that. But this is just an estimation. I mean, these gases are not prepared by cooling from the liquid.
Much smaller. Okay. And here we see what kind of it's a in specific heat. It's a glass transition or it's a phase transitions. What this feature we have?
Well, this will be a glass transition. Okay.
Okay, it's glass transitions, and we see the difference for fast cooled and ultrastable glasses.
Sure.
For fast cooled, this temperature is the same for all samples, and for ultrastable, we can see some shift with depending on the thickness of these glasses.
Yeah.
So,
But
can you add some comments? What's the role of thickness? Why this shift we observed for ultrastable glasses?
so you see, no, this ultrastable glass does not transform via bulk mechanism because the surface is free. No, we saw here in a previous slide. Let me look for this. No, it was here. No, so the glass transformed not from the bulk but from the surface. Okay. Now, if you take the heat capacity different thicknesses, and here this is a specific heat. So this is the heat capacity divided by the mass. Okay. So what you are doing here is it's not a right normalization because you can divide the heat capacity by the mass when the process depends on the mass. But in this case, the process does not depend on the whole mass of the sample. No, because you can have a very thin layer and you can have a very thick layer with different mass, but the transformation will take place in the same way. So a front starting from the surface and propagating into the bulk. Okay, so somehow if you divide by the mass, you are let's say you have something which is not real. So this size effect you see here is not real. It's a consequence of a bad analysis of the data.
Oh, okay. Thank you for these explanations.
Yes.
So, dear participants, if you have some questions, please react in some way. Would you like to ask or add some comments? I have 2 questions, maybe. 34 slide.
4?
34.
34.
34.
Here.
So, so probably you already explained this shift.
Yes, exactly. This is let's say a way to see this shift is a way to see that the transformation is taking place via front from the surface. Okay.
Okay. So, and slide 61, the last questions. Some couple of questions here. First of all, it's all these conventional glasses, ultrastable glasses, it's for the same material in the medicine.
Correct.
Okay. And temperature of glass transitions for conventional glass, ultrastable glass 2, different.
Yes.
So can you say the values of this temperature of glass transitions, and what your opinion about correlations of the effect that you observed in the low temperature heat capacity? Is it in some way can be correlated with this temperature of glass transitions, or it's not same subjects, it's different subjects?
Well, here in this case, in ometacine, the TG of the ordinary glass, let's say, is 15, as you see here. In the case of the ultrastable glass, if I remember well, it's 340, something like that. So like 30 degrees of difference. Okay.
Okay. Your opinion, is it possible it's reasonable find some correlations between temperature of glass transitions and effects that you observe at decrease of the boson peak.
Well, we tested so far two materials, no? Indometacin, which is this one 315, and we also tested the TPD, no, which is the other one, which has a TG of 333. Okay, this one, no? And in both cases, we see the same. So we see a suppression of the TLS in the ultrastable state. Okay, so if you mean a correlation with the TG of the original material, I would say there is no correlation because in both cases with different TGs, we have a completely suppression. If you say a correlation with the TG of the vapor deposited glass, then I would say yes, no, because the glass transition temperature of the vapor deposited glass depends on the stability, no? So the higher the stability, the lower the amount of TLS in the system.
Okay, thank you. Mm-hmm. So probably if no questions from the other participants of our seminar, we ready to close remarks. Dr. Cristian Rodriguez-Tinoco, thank you very much for your excellent talk, for your answer on the questions and these insights of the physics of ultrastable glasses. We also thanks to the National Research Foundation for Ukraine for support our seminar series. We also thanks for defenders of Ukraine, and thanks to all participants for engagement in our scientific seminars. We look forward to see you at the next seminars.
Thank you very much, Maxim.
Thank you.
Thank you. Bye-bye.